Professor, hello.
Hello. Hi, Antonella. Hi, everybody. Wow, Albert is here.
Hello.
Hello. Hi, Vitello. So happy to see you all. Oh, Vladimir also. We have a beautiful audience, Ozaki Sensei.
Hi, Professor Chinkova.
Congratulations, Ozaki Sensei, on the huge award. I'm so happy
to kind. Thank you very
announce
much.
This. Professor Ozaki received the Emperor Award this month.
Thank you.
It's a huge contribution to Japanese society. And not only for Japanese society, for the world.
For the science.
For science.
Yeah. Yes. Okay, I think we can begin. We are like 3 minutes. Professor Tenko, would you like to start to address people?
Yes, with pleasure. It's really my pleasure to welcome everybody, and especially to have the talk of Antonella. It has been a long plan and expectations for this talk, and I'm very happy that we have so many people coming from water science society also, and Aquaphotomics joint efforts to get the truth about water. So I'm really looking forward to this, Antonella, and thank you very much for agreeing to give this talk. Okay.
Yes, thank you. So I would also like to repeat, we're very grateful, Antonella, that you accepted to actually give this webinar. And this is a really very interesting topic. Because it is a quantum, right? And you're going to talk today to us about, I think, the topic that really interests, not only, I see a lot of people coming here from, that I know from Water Conference. Hello, Pierre. Hello, Evelyn. You're very, very welcome. I'm glad to see you. So this is a little bit a topic maybe which is a new for Aquaphotomics community, but it is very important for us to, let's say, move from the traditional way we see water, like just this molecular aspect to the quantum aspect. So we have like 30 to 40 minutes for your lecture, and then during the lecture everybody can, for example, type the questions into the chat box, and afterwards we will have a live discussion. So Antonella, thank you very much for accepting this and being today with us. You may begin if you want to share your presentation.
Okay.
And it would be nice if everyone turn on their videos. It is much better, how can I say, feeling when a speaker can see you.
Yes, please.
Thank you.
Can you see it?
Yes, it's perfect.
Okay. Okay, first of all, thank you very much for your invitation to this webinar. I'm very happy to have the opportunity to make a review of my last 10, 15 years of work. And so it has been very useful for me to do this review. So thank you very much for this opportunity. And title of this talk is the two fluids in liquid water. I'm not a theoretician, so I will not spend much time in describing theory, but I want just to drive you in a walk through several experiments I did during the past 15 years to show if the two fluids theory could be supported by the experiments. And my personal view is that looking carefully at the experiment in a critical way, it's quite obvious that water is made up by two different fluids. And just a moment. Sorry. Okay. So the summary will start from describing why we expect two phases in liquid water. And then we'll start from the vibrational spectroscopy to understand what can be actually seen by the experiment, and what is the isosbestic point and why it's so important for understanding the problem. And then we will move to the analysis of the solution, the aqueous solution of strong electrolytes that are very interesting in order to see how water arranges in cases of perturbation. You can just imagine that the solute is a perturbation in the organization of water. And then we will see that there is a kind of special arrangement of water that is not trivial. There is a self-similarity in organization of water on large scale. And then we will see what happened to the dielectric permittivity. Okay, these are the anomalous properties of water that are mainly based on structural fluctuation. Water is a so-called a cool topic in modern physics. It's very interesting. And this is a very important paper that has been published in 2009, pardon. And you can see here the typical anomalies of water, that is isothermal compressibility, heat capacity, and thermal expansion. You can see what happened in case of a typical liquid, and this is the behavior of water. This is heat capacity, a typical liquid, again, the behavior of water. So what can you see here is that all these thermodynamic properties measure the response to an external perturbation, such as temperature, pressure. So these are thermodynamic response function. And water has an unusual behavior with respect to this perturbation. And this anomaly becomes much stronger on cooling. In fact, you can see when fitted to a power law, each of these properties seem to diverge towards a temperature of 228 Kelvin. There is a divergence, but why? So this is a picture that has been proposed by Nilsson and Pettersson in 2015. And Nilsson and Pettersson are two of the most distinguished scholars on this topic. They are very, very known in the world of water. And they assume that these properties are connected to mainly to the ability, the possibility of water to form up to 4 hydrogen bonds with other near water molecule. And the fluctuation of this possibility of arrangement give rise to the formation of local structure that can be an homogeneous liquid of type 1 or type 2, or a mixture between them. And the collective motion, the time scale for this collective motion is expected to be in a range of picoseconds and varies with the temperature. This is what has been proposed, and this is the most interesting model that has been proposed about water in the contemporary literature. So everything stands on the hydrogen bond concept. The hydrogen bond is very, very known, of course. It is the possibility of each atom or of each molecules of water to form a bond between oxygen and the hydrogen of another molecule. Each molecule can form up to 4 of these hydrogen bonds, and these bonds are very weak, so they can be break and reformed in a very simple way. But now, what we can propose is just to reverse the statement that the hydrogen bond is the origin of the collective behavior of water. We have seen in a previous slide that has been proposed that the hydrogen bond is at the basis of the collective behavior of water. We say no, it's the collective behavior that is at the base of the hydrogen bond, that is a phenomenological bond. So the existence of a collective ground state different from the ground state, so the existence of a collective ground state that is different from the ground state of an isolated molecule, as is predicted by the quantum field theory, is the physical cause of the phenomenological concept of H bond. So we start from the quantum mechanical and we arrive to the hydrogen bond. Of course, we have no time to enter in detail into quantum mechanics, but what we can say is that the simple idea is that the ground state of an ensemble of molecules should be different from the ground state of an isolated molecule. What does it mean? It means that in order to have a complete description of condensed matter in terms of quantum electrodynamics, we have to consider particles and electromagnetic field. With this starting point, we can arrive to the description of a different state of matter that is the real ground state of the matter. And this leads to the appearance of a ground state whose energy is lower than the energy of the ground state calculated for an ensemble of non-interacting particles. So we have to assume in the description of our state that the interaction, the electromagnetic interaction of all the ensemble. So this is the dynamical base of the long-lived tetrahedral model. One of the main problems in approaching the hydrogen bond model, the tetrahedral model, is that in order to build a correlation, a long-range correlation among many molecules, it's necessary that the hydrogen bond lasts for a long time. If the hydrogen bond is a weak, as it is a weak bond, it cannot last for a very long time. So it's quite impossible to imagine that many molecules are connected through a weak bond. We reverse the formulation and say that molecules in condensed state are in a ground state which differs from the ground state of the isolated molecules. Then doing calculation, we can see that the electron clouds radius of the coherent state is higher than the radius of the non-coherent states, and it shows two maxima angled at 109 degrees. And this direction forms a set of tetrahedral axes which can account for an hexagonal configuration. We can see it better in this picture. In a non-coherent state, the calculated electronic ground state of water molecules has a smooth structure like this one. Change again. This is more or less the electronic clouds of the ground state of the isolated water molecules. In case of collective states, the electronic clouds is this one. If there is someone interested in the detail of the calculation, this is the reference. So what is important is in this state, there is no way to found a particular direction. There is no way to found anything who can describe the hydrogen bond. But if we start from the collective ground state, we see that there are two particular directions. This direction are the direction of the bound, of the hydrogen bound. So everything in this perspective, everything has a very as a more rational explanation. Even the hydrogen bond has a rational explanation in the coherent state description. But now it's time to move to the experimental aspect, the experimental consequence of this description. And we start from the vibration modes of water molecules. This is a very well-known picture. This is the infrared spectrum of water. This is the bending peak, and this is the OH stretching peak. What we can learn from this? Now, what can be explained with the continuum model? The continuum model is the model that is uniquely based on H bonds between two molecules of water. What we can explain? Oh, okay, we can explain the dynamical effect in the line shapes, introducing a parametric model. We can explain why the peak, the stretching peak is so broad, the broadening of the stretching peak, because it's possible to make simulation on the basis of 122 about molecules, and we can describe the broadening of the peak. We can also describe the existence of non-hydrogen bonded molecules, I mean dimers or monomers in water. But what we cannot explain the existence of an energy gap independent on temperature between two distinct populations of molecules. And we cannot explain the effect of solutes on the line shapes. So we see why. So what you can see here, the black line is a typical stretching peak of water. So this is the OH stretching peak, the black line. The red line is the fitting that we can obtain using a single Gaussian. So the single Gaussian can get rid of the broadening due to the fluctuation, but it's not a good approximation of the peak. Actually, we see something different of the Gaussian broadening of a line. In fact, if we want to have an approximation, a good description of the peak, we have to use at least 3 Gaussian. The convolution in 3 Gaussian, in 3 subbands is univocal, because 3 is the minimum number of subbands that we can apply, and it is physically meaningful. Of course, if we use the convolution using 4, 5, 6, 10 subbands, sub-Gaussian, we can have an even better approximation, but it has no physical meaning. So 3 is the minimum number that have a physical meaning and gives us a good reproduction. In addition, we can see that if we apply a second derivative technique, if we take the second derivative of the peak, we actually have 3 minima, and the 3 minima correspond exactly to the 3 maxima of the 3 subbands.
Antonella, can I ask you something?
Yes.
Sorry. I understand about the 3, but I wonder why can't we have more than 3?
More than 3 is just a mathematical application. If we want to describe, if we want to make the description of a peak, of a curve, if we use many Gaussian, is a central limit theorem in statistics. We can
I understand that, but I go from a physics point of view that
meaning.
If we have different level ground states, then we could have them, we can see them here, those many ground states, don't we?
No, there is only one ground state. No, sorry.
Okay. So we'll continue at the end, yeah.
Can I go on?
Yeah, please. Yes.
Okay. So this is what we get if we apply a simulation. We use a simulation, a simple point charge standard model for simulation. But all the simulation contain a heavy hypothesis. The absorption line is described by a time averaged frequency of the fluctuation, where the time of integration is the parameter adjusted by the field. What does it mean? I assume that the broadening of the peak is due to the fluctuation of the frequency of the fluctuation. But in order to have a fitting, I have to make an integration of this fluctuation, sorry, over a characteristic time. This time is the parameter of the fit. So it's a kind of circular reason, is a circular thinking, because the parameter is adjusted on the experimental results. And so this is the reason why the simulation is not so useful in order to fit the experimental data. You can see here the difference between the experimental data, and is the pink curve, and the blue one is the result of the simulation. So is the reason why we propose to fit the peak of the stretching peak of water using 3 bands. The first one, the red one, that is a lower energy subband, describes water molecule having a high correlation with their environment. The blue one, that is higher energy subband, describe water molecule poorly connected, and there is an average degree of connection in between. You see that it remembers closely what has been proposed by Peterson and Larsen here. And you see that we have 2 different well-assessed population, and there is something in between that is regulated by fluctuation. But this has been proposed in 2001 by Bruback and his co-workers. So it's not a new idea in spectroscopy. And we will start from this assumption to go on and to develop our model of water. So we see here what is the, let's introduce what is the isosbestic point. Isosbestic means equilibrium point, and isosbestic points are commonly met when on changing a parameter occurs a reaction or a phase change. I mean, I'm changing the temperature in this picture, and something is happening in my system. There are 2 absorbing components that are in equilibrium in this point. This point is the same absorption point. Isosbestic means same absorption point. And so we have the 2 sides above and below this point that are reacting in a different way to the perturbation that in this case is the temperature. You can see here that the red curve is higher in this part here and lower here. So here is increasing and here is decreasing. So there is something that is growth in this part and decrease in this part. So we define the isosbestic point in this way. So this parameter here is the absorption of the OH stretching vibration of water in the band we are considering. And we define an equilibrium constant that is the ratio between the area under the curve below the isosbestic point and the area above the isosbestic point. So why the area? Because the area is just the number of the chromophore which are absorbing in this region. So we can say that if A and B are single chemical species or different phase of a single substance, and their absorption spectra intersects at an isosbestic point, we can say that A and B are in equilibrium at their concentration are controlled by the running parameter that can be temperature or solute concentration. Maybe we can see better here. So in this picture, we can see that we have two different populations that react differently to the temperature, but are in equilibrium. Now, let's assume that our system is made up by two states, the states 1 and the states 2. And the two states are reflected in the area above and below the isosbestic point. And they are separated by an energy gap, delta E, so according to a Boltzmann statistics. If this is true, this system exhibits a Van-Hoff behavior. So the equilibrium constant of the reaction has to fulfill this relationship here. So this is the Gibbs variation at the equilibrium. So this must be valid. This is just derives from this one. This derives from this one. And in fact, this is what we get if we plot the ratio between the two areas, the red and the blue in the other slide, versus the 1 over T over the temperature. In fact, we have a linear behavior. This linearity implies that the energy gap is independent on the temperature. So we have two populations which are in equilibrium on varying the temperature. One population increases while the other decreases if we change the temperature, and their energy gap do not depend on temperature. This is also confirmed by the near-infrared spectroscopy. We can obtain similar behavior even in the first overtoned region. Even in near-infrared spectra, we can apply the second derivative analysis and show that we have two modes can be assigned to water molecules. And the Van-Hoff behavior is observed even in the overtoned region. In all this slide, I put the reference for each one of this topic. Now, we have changed the temperature. Now we change something else. That is the addition of solutes inside water. And we start to observe what happens if we had some chlorides in pure water. And we observe the existence of a very clear isosbestic point: lithium, sodium, potassium, and cesium chloride. This is absolutely clear. And if we look deeper inside this point, we can have very interesting information about the dipole of water molecule. Why? Because the maximum of each subband is related to the length of the OH bond. So the variation of the OH bond length can be evaluated by the shift of the center band frequency from this relation here. So if we observing the spectra, we can observe that the center band shift toward blue or toward red in a different way. I mean, each one of these subbands behaves differently with respect to the solution of solutes. We can assume that at zero concentration, the length of the bond coincides with the length of the ice or the vapor. The ice for the lowest energy band, for vapor for the highest energy band. We can evaluate how much the OH bond length changes when we add solutes into water. And the changes are different from the different peaks. In this way, we see that for the first peak, that is the peak related to the highly correlated molecules, the length decreases, increasing the molarity of the solutes. While on the opposite, the length increases when we had solutes to the less correlated fraction of water, that are the quasi-free molecules. Almost anything happened to the intermediate band, because the intermediate band is due to the mixture of the fluctuation. So the average of the fluctuation is almost zero. But it's very interesting to observe that on the most correlated part of water, when I had the solutes, the interaction among molecules increases more than the interaction between water molecules and the molecules of the solute. So there is the molecules are strengthen their bond. This is what happens to the area of the peak. The area of the first peak decreases, so we can say that the addition of solute destroys the correlation in water, and increase, of course, the amount of water that are poorly correlated. Again, there is an average effect in the intermediate fraction. Now, since our system is a superposition of two components, where the real sum of the density is conserved, we can understand the real meaning of the isosbestic point in water spectroscopy. The two phases in water behave differently with respect to solution of water, of ions. In one phase, the water-water interaction prevails on water-ion interaction. In the other one is the opposite. So they are actually two different components in water. And the effect of solutes at this point can be barely regulated within few hydration shells. What we have seen is that the occurrence of the isosbestic points on the scale of the wavelength follow the same order of the Hofmeister series. It is a series that has been thoroughly investigated during here in order to understand its meaning. Being the isosbestic point related to the ratio between the low density and high density fraction of water, we should expect a relationship between the isosbestic point and the solution and the density. So we can use the isosbestic point as a predictive instrument in order to understand what will happen to the density of the solute. We have an isosbestic point even in halogenic acid, but the meaning is quite different. We see that there is an equation for the isosbestic point. Is it possible to have an equation in order to predict where it will be the isosbestic point of my solution if I know the molarity of the solution and I know the parameter? I know, of course, the parameter of the solution. I mean the electric charge of the solute and the radius of the anion and the cathode. What is important to say is that the first term, this first term, A is a parameter. The first term is multiplied by a factor that takes into account the inverse difference between the electronegativity of oxygen and the electronegativity of the anion on the solution. And the electronegativity is the force of attraction of an atom for bonding electrons. And what is interesting to see is that fluorine is the only anion which has an electronegativity that is higher than oxygen. And this explains why this fluorine is so different from the other in this family of curves. The second term here strongly depends on the anion size, and this second term, pardon, this here, from the radius of the anion side, and there is an upper bound for this term here. This term here is exactly the difference between the electric field of the anion and the cathode. So this confirms that the electrostatic forces are the leading forces, not only in the solution formation, but also in the restructuring of water due to the solutes. As an addition, this equation allows also to determine the molarity of a known solution just with a single spectrum in infrared. Because if I know the spectrum of water, I just need to take one single spectrum of my solution, having an unknown molarity, just look for the isospastic point, and then I can find the molarity of the solution here, just with only one measure. So it can be also used for a very rapid way to determine the molarity of a solution. This is a comparison between calculated and measured isospastic point using that equation. We have not much time, so we have to go quite faster on this point, but the matching is acceptable. We can also determine the density of the solution, just knowing the isospastic point. And we know that the isospastic point describes how water molecules modify their OH bond length to face the complex electrostatic force balance due to the solute. So the isospastic point is really a crucial point to understand water. So we can thus observe that the density of an electrolytic solution also depends by order-disorder degree of water induced by the electrolyte on the long-range structure of the liquid. So it's not just the problem of how many shells of electrolytes are around a single water molecule, but it's a problem that is connected to the restructuring of the whole water around the solute. So the experimental observation of vibrational spectra of strong electrolyte solution suggests a self-organization of water molecules depending only on the concentration and not on the ion's nature. Three different regimes can be observed. At very low concentration, ions shielding does not change the water molecules in intramolecular bonds. Whenever the concentration increases, a distortion of the vibrational peaks is observed that increases linearly on a log-log scale, and then the deformation arrives to a maximum deformation limits. So we see that when we had a solution in water, we observe a general restructuring of all water. And there are three different steps in this, depending on the molarity. Again, if we introduce a deformation parameter, that is the ratio between the two areas above and below the isospastic point, this is the behavior that we observe when we had solution in water. There is a first region where almost nothing happened. That is, there is no restructuring of water. And this is normally is the field of application of the Debye-Hackel equation. Normally, the Debye-Hackel equation, normally this equation implies that, that there is an ion with these electric clouds around, and the other ions are arranged around the central charge, electric charge. This has an application only in very, very low molarity, in the order of less than 0.01 molar. That's about this region here. So the region of application of the Debye-Hackel equation is this one. There is no restructuring of water. But when we arrive at high concentration, about 1, more or less, it depends on ion, we have a dramatic change in the restructuring of water up to a maximum limit. This is the limit. This is the limit of the solubility of ion in water. What is very interesting to observe is if we plot the previous data in a log-log scale, we obtain a straight line. And the slope is almost the same for all ions. Now, the straight line fitting can be represented by this equation here, that is the same as this. And this shows us the scale-free nature of this rearrangement of water. This relation here is the relation that is typical for fractals, for self-arrangement systems. This coefficient D is called fractal dimension. So we understand something more about how water restructures when we add solution, when there is a perturbation. This is very interesting. Why? Because scale-free networks that are described at these power laws here are not just a change in the we cannot move from how to say, this is a complex system, and we cannot change a system that is arranged in an exponential way to a system that is organized in a scale-free way. It will be more clear in this example here. This is the example of an exponential network. An exponential network is each point is connected to a certain number k of other point. It has a number k of links. In this case here, you can see that we have about 3 links for each point, and in fact, the probability of the links is a peak around the number that is 3 in this case. In case of scale-free networks that are described by a log-log law, as we saw in case of water, the organization is completely different. Each point is connected to several other points. In other terms, there are hubs. These points with the red points are hubs. Each point is connected to more, where k is the number of links. This point has been treated by Barabasis and other co-workers in a very famous paper published on Nature in 2000. That I recommend you to give just a read to this paper, because it's very important. It's it opens your mind in many aspects. Now, what does it mean that we have self-similarity in water structure? Well, scale-free models are present in the biological realm, in cellular metabolic network. Each cell is a node, as you can see in this picture here. It's found that most molecules participate in 1 or 2 reactions, while few, the hubs, participate in many. So in the biological realm, there are molecules that are more important than the other, such water or ATP. Water and ATP participate in more reactions at one time. And the auto-organization is the result of a dynamical process based on the interaction among components carrying out a configuration having properties different from the original one. I mean, the difference between one bird and the flock of birds that moves as one. So when the system has an auto-organization properties, it behaves in a way that is completely different from the way of behavior of a single component. There's something more. Giuseppe Vitiello has shown that the auto-organized systems are also quantum systems. But this is a detail that we have no time to cope in this presentation. Now, the last point is the electric permittivity. So the electric permittivity is the capacity of a system to relax after the exposition to an electric field. So the Debye model, that was the first model proposed, the first and the most useful model proposed at the beginning of the last century to describe the electric permittivity of water, describes water molecules as non-interactive interacting dipoles subjected to an electric field, and there it studies the relaxation. In order to explain the data, these are the data of the dielectric expression of water. This is the real part, is a complex quantity. This is the real part, this is the imaginary part that is related to the dissipation, so the absorption of water. This is the experiment. In order to explain this experiment, it has been used the Debye formula, the Debye model. But the single Debye function fits the data up to 100 gigahertz. When we move at higher frequency, the data are no more, we cannot fit the data anymore with a single Debye function. So it has been proposed to use a double Debye model. Right in this way. So there are two constants of relaxation and an intermediate, this epsilon1 parameter that has been introduced just in order to fit the data. There is no consensus on the physical nature of this proposal because nobody knows what actually are these two terms. But it worked for a certain times up to the time when it was possible to take measure at frequency higher than 1 terahertz. At this point, even these two pieces were not more useful to fit the data. There are other open problems, that the data are not there are many scattered values moving from one experiment to the other. There is a problem with the residual polarizability at higher frequency, the epsilon to infinite, and it is different from the refractive index. So there is an open problem. But we propose to move from this step, from this equation here, to this equation here. It seems almost the same, but is very, very different. Because we suppose just to use the single Debye model, but applied on a different system. A system composed by two non-interacting populations. We have two populations. We have seen in other experiments that water is made up of two populations. We apply the single model, the single Debye model to these two populations as a linear combination of the two, where this parameter n is the coherent fraction and 1 minus n is the non-coherent fraction that we have measured in the infrared measure that I showed you before. So, using this step, we were able to fit all the data up to about 2 gigahertz. The red one, the red point are our data. The blue are the data obtained in a lower range of frequency, and the black line is the fit function, and it fits perfectly all the data. It is interesting to note that the ratio between the two constants, this is the zero frequency, is the static dielectric function. The ratio between the dielectric function of the fraction 1 and fraction 2 is the same as the ratio between their relaxation time. This number, R, we call it R, is 26 for pure water and decreases with the concentration of the solute because we are changing the ratio between the two populations. There is something more interesting in this formula here, is that we had to add this small term here in the imaginary part of the dielectric permittivity. This seems just a details, but it's not a details. Why? It is the violation of the non-locality. We had this small term here that is a violation of the Kramer-Skrening relation for a very small time, that is about half picoseconds. The Kramer-Skrening relation expresses the real part in terms of the imaginary part. It's a general relation, but it's very important because it links the effect of an electric perturbation at the point x and the time t, but it's due to an electric field that was generated before at a time t minus tau. So it's just a signature of the causality, a causal link, causal link between this is the cause and this is the effect. And cause and effect must be related by a very clear time relation. So what is happening now must be produced by something that has been produced before. And we observe a violation for a very short time, but there is a violation of this principle. But which kind of system can stand for such a violation? How is it possible to have this apparently non-physical results? This is only possible in systems where information propagates simultaneously. That is a single-state quantum system. So this is another hint that we are dealing with quantum system, that in water there is a quantum system, and it's impossible to avoid this description. Now, we refine the data, we check our data even in checking the permittivity of chloride solution, and the data are absolutely satisfactory. We were able to fit with our two components, with the two models, all the data for all the solution. And we were also able to explain the strange behavior of lithium chloride. Lithium chloride is the only salt that shows dissipation lower than pure water. It's more transparent than water. We add lithium, we add lithium to water, water is more transparent. It is very strange. It was not understood up to now, but it is due now. We know why, and we know that lithium has a great caltropic effect. It has a very effect of disordering the structure of water, and this because it's high charge density, because lithium atom is very small and the charge density is very high. So it has a very caltropic effect on water. Now, we are to the conclusion, and we have seen that the infrared spectroscopy allows to gain many information about the intermolecular structure of water. The deconvolution of the broad OH stretching peak allows to identify population of molecules having different degree of correlation, then supporting the picture of two phases in liquid water. And the spectra are very useful to study the solution of salt, and it can shed a light on the problem of solvation. Solvation has not been studied using the infrared spectroscopy up to now, but spectroscopy has shown, the infrared spectroscopy has shown that it's very, very powerful in order to understand the physical mechanism of solvation. Also, the near-infrared spectroscopy confirmed the results. Then we observed the self-similarity in water solution. And self-similarity supports the hypothesis of an underlying quantum dynamics that is also confirmed by the measure of in the terahertz spectroscopy. And so the coexistence of two populations get rid of the problem of the unexplicated permittivity of water at very high frequency. And this is the conclusion of this talk, and it's also the conclusion of my work, experimental work on water. Thank you for your attention.
Thank you very much, Antonella. This was really nice to hear, and you clarified a lot of things that I personally had some difficulties understanding before. So we can now answer questions from the audience. If you want to have a question, if you have a question, just raise your hand on Zoom, or you can type. Come on, don't be shy. Okay, Professor Vitiello, please just turn on your microphone. Thank you.
Yes, thank you. Just because it's okay. Mine is not a question actually, but just before Antonella was mentioning about such a term, that small term, as you were saying, Z omega, something like that. Indeed, that is an entanglement term. The word to be used is entanglement. When you say that it is just one quantum system, that is a very interesting point. In fact, is a term which comes from the entanglement, which is the usual word, I mean, today is used for that, between, I suppose, the two phases, because one is the environment of the other one. You had n and 1 minus n in your formula of this, your version of the 2 Debye system. Yeah, so that was just to mention. I mean, your observation to me sounds in these terms. Yeah. Thank you.
Okay. Thank you for the comment. Yes, Professor Zenkova, please just turn on the microphone.
Thank you, Antonella. I'm happy Vitiello is here and you're here, and so we can think together. What we have in our data, and what is interesting is that we have exactly what you suggested. We observe coherence in water. Non-coherence is only in a specific, very small wavelength range, and this is around the isospecific point, which means that the frequency of isospecific point is non-coherent. I mean, it's a frequency of non-coherence, or whatever you call it. But the interesting thing that I still cannot explain is that the correlation, this log-log plot, the correlation in these two areas, as you mentioned, Antonella, they're called less hydrogen bonded and hydrogen bonded. They're called different names, but they are two different liquids, as you call them. And we find a positive correlation in one of the areas and negative correlation in the other in the other area. I'm talking about the correlation between optical density and log of the temperature. So this is exactly what you explained, n and 1 minus n. So we have two liquids, you call them liquids, and those two liquids are coherent, and we have a negative correlation for one of them and a positive because they're complementary, probably on the other side. Our non-coherent point is the isospecific point. So I'm bothered only by the minus in correlation. How can we explain this, and is it okay, or what is your opinion on that?
Sorry,
I don't think that one liquid is okay for people to understand. Less hydrogen, so-called until now, less hydrogen bonded water is non-coherent. I don't think so. No, it's not that I don't think. Our calculations do not show that. So we have correlation in less hydrogen bodied water as well.
We have correlation in
Log plot. Yeah.
In the log plot.
Yes. Yes.
Okay.
Yes.
And then in water we have anyhow two population. In pure water we have two population. When we start to add solutes in water, there is a perturbation of the ratio between the two. And when the solutes are, but when the solute is small, with the amount is small, there is no deformation of the structure of water.
Mm-hmm.
More or less, the amount of correlated and non-correlated water is unaffected by the solute, up to what was called the bivouacle approximation. When chemists usually use the molarity and not the activity of the solution. Then, you know, at a certain point, when the molarity is high enough, you have to change and not use the molarity, but you have to use the activity of the solution, because there is something that is changing and you have to take in consideration something else, and not only the electrostatic feature of your solution. And so the chemists have invented the activity of the solution. And so you see, if the solute is small, more or less the structure of water is unaffected. After a certain point, there is a restructuring of water. And this is the increase in the curve. I can show you again the picture.
Yeah, but I think the concentration, the topic of concentration is very, very interesting, is a good word, because what we observed and the dilution problem is related to this. We have a very low concentration that restructured water immensely. Yeah, we can see this.
Okay, we're talking about this picture.
Mm-hmm.
Liana, can you see the?
Yes, I can see it. Yes.
Okay, so in this region here, almost nothing happened. The ratio between, so the deformation of this peak is almost zero, you see. So the ratio between the blue and the red area is unaffected. After a certain point, there is a rearrangement, a general rearrangement that is all and the growth of this curve is almost the same for all the salts which are for lithium, for sodium, and so on. So this means this applies to me. This is the log-log representation of the curve of the other picture. So this slope is almost the same. That implies that is a general restructuring of water. All water is restructured, and the ratio between the two populations does not depend on the local properties of ions, but it depends on something else that involves many, many more molecules. I
absolutely agree with this. Absolutely agree with this. There's no, though when we go to lower and lower concentration, maybe we're going to see different effects, but that's another topic. Yeah.
Thank you. May I just comment, because it is related to what Professor Tsenko was asking. What would change if there is actually, if we do not have a really true isosbestic point? I mean, I didn't see, for example, how it looks like when you maybe zoom in your spectra in infrared. But what if there is no true isosbestic point and it actually changes? It actually has a, let's say, it moves, the location is within some range of values. what does it mean for that system? Would it mean that there is some kind of third?
Why does it move the isosbestic point or the maximum of the peak?
Isosbestic point. So, for example, what would that mean if there is no true isosbestic point? If the actually isosbestic point is not a point, but has a function, has few values, can have few values actually.
Okay. It depends. It depends on ion. In some case, you can see a real isosbestic point. I mean, there is just one point. It is very net crossing between among the several curves. There is some cases in where there is a small range.
Yes,
so,
yes.
So depends on something. I've never seen it in using strong electrolytes. Is it possible to see other cases? But now, I'm sorry, I don't remember. I remember that there is a paper that has been studied by, it's theoretical studies, that explains what does it mean if there is not a point but a range.
That would be fantastic if you can share, if you remember, and if you can send it to my email. I would love to see that paper. I do not have any explanation, and I was wondering, for example, what would this mean?
I'll send you the paper.
Thank you so much.
Problem. I'm sorry, but I don't remember.
No problem, of course. I mean, I don't have any information. I at least now know who has information, so you gave it to me. And I wanted actually to ask one more thing. You said you on one slide you provided these log plots, and I was wondering, you did not provide a value of fractal dimension. Do you remember maybe what was the value? What was it, like 1 point something? How much?
I don't know. It's something. Yes, it's something about. Just looking at the picture, something that is less than 1, of course. Something in yes, it's less than 1.
Less than 1. So what would be a physical meaning of this? Because I know, for example, if I have a fractal dimension of an object, let's say some geometrical pattern, so the higher the dimension is, this pattern fills in the space better. So if it is more towards 2, it means that it almost completely covers the surface, while if it is closer to 1, it is. So what would be that kind of, what would that mean about water, for example, this value of fractal dimension?
I don't know.
Does it have some kind of meaning?
Property of water, maybe Peppino can say something more openly.
Professor Mike,
yes,
sorry.
Yes, it affects the degree of coherence.
The degree of coherence.
In this case, about water. So this is why it is the fractal dimension is related to what is called in a quantum, how to say, jargon, a quantum deformation, a Q deformation of the coherent state. So if you have a coherent state, let's say usually in the books, alpha is the, think of a Glauber coherent states. Then if you start with alpha, and then if you have some deformation, that alpha will be changed, will become, let's say, Q times alpha. That Q is related to the fractal dimension. And what you are saying that your, how to say, phenomenological appearance of the fractal, in one case it covers, invades the full region, in other case it shrinks or does something, that is just a reflex at a reflection, at a manifestation at the macroscopic level of the coherent state at microscopic level. Because we should always remember that coherent states are the most near states to classical ones. So we are actually dealing with something like an order parameter. So when we see such a kind of a beautiful graph that Antonella got, these beautiful straight lines with very small mistakes, by the way, errors around the straight line of those points. Antonella, you have, I don't know how much it is because in the pictures there are no indication of the errors in the measurement, but they are very near to the straight line. So this means that you have really a self-similarity, a scale law, as Antonella was showing. This is a modification of the coherent structure, depending on the boundary conditions, the density of the solute or whatever, the characteristic of the solute, because those pictures, Antonella, they were one for K, one for potassium something, another one for lithium chloride. I don't remember now, but they are for different. Yeah. By the way, I would like also to make a very short comment on Rumiana observation. I think that really we could have different liquids, always water, of course, but different phases of water, even with a different degree of coherence, not necessarily one coherent and the other one not. That is, in some sense, an extreme case. But since we can modulate the coherence in some way of water, then we might have a highly coherent region floating in a less coherent region, which, if I understood, is what Rumiana was saying. But that is consistent, fully consistent with this multiple phase, not just double phase of water. That is even more.
Yes, yes, I absolutely agree. Thank you, Vitiello. Because I think what is...
Sorry, could I jump in and ask something that...
Yes, of course, Alexander.
Yeah, to Vitiello and also.
Hi, Alex.
Hi, Rumiana, thanks. Great talk. I'm super amazing. Thanks, Antonella. And so I want to go back to the point of your fractal dimensions and the point you made about hubs. This is exactly the point being discussed. And if we understand that our vision of water should not be that is, there are like domains that are equivalent around, but more of a hub way of understanding the connection, then that really changes how we should picture the water. As it's a very, if we take what you're saying about scale-free invariance to be true, then we can't think of that picture of localized quantum coherence domains that I have about 100 nanometer across. And that's what we've been thinking. So I'm just putting the question out there. Should we be thinking about the coherence in water as this scale-free invariance hub-based network rather than the old picture?
No.
So that's the question.
So, Antonella, can you answer?
It's not just a question, but so a comment on that. The problem of coherence. So, what is a hub? The concept of a hub is not related to a coherent domain, but it's just related to a single molecule. The single molecule behaves like a hub. So there is a collective behavior in water that connects water to others. So when we look for the chemical reaction, even in the realm of biology, we have to keep in mind that water behaves in this way. So we cannot extrapolate the behavior of the single molecule. We have to keep in mind the behavior of the whole organization. So this is the message implied in the restructuring of water in what I show. Is that we have to abandon the idea of a single molecule.
Okay, you're saying it
must be substituted, must be changed toward the vision of a reorganization of the world.
Yeah, but it's not necessarily linked to the whole coherence aspect. The two are not necessarily linked. So it's a property of whole biodynamic processes, this scale-free invariance, but the whole discussion about coherence is somewhat separate. Is that what you're saying?
No, since there is a coherent fraction in water, this coherent fraction interacts continuously with the non-coherent fraction. We cannot separate the behavior of the coherent and non-coherent. They are linked together. And there is a rearrangement of the whole structure where one increases and the other decreases, following a certain law that is the free-scale law of the system. So when we want to describe the solvation as example, but we cannot assume that there is a single water molecule and several shells of solutes all around, because it's not describing correctly the situation. So the situation is that when I had the solute, there is an electrostatic perturbation that modifies the structure of water, of both the population of water. If changes one, changes the other one. In a very clear and very well structured mode.
Okay, I'm sorry, we have a Professor Boyko. Yes, please.
Thank you very much, Antonella. It was just very brilliant and explains a lot of paradoxes in water and solutions. But still, I have some problems, and I think not only I, with the properties of ultra-high dilution. Ultra-high dilution. Yes, potentiated properties, which were shown, for example, by Cannavalo, that that below certain concentration or dilution, the properties of aqueous systems, they change dramatically in a just a phase transition happens. And this phase transition depends upon the environmental electromagnetic field. If you put this system into the shielded place, then all the paradoxes disappear in ultra-high dilution. So does your theory at least expect the effect of external electromagnetic fields upon a liquid system? Second question is, which bothers me more and more, that is the ortho and para waters, which just pre-exist practically in all waters, and their ratio is rather substantial, the 30% up to 50% or one.
Professor White, we lost sound.
Do you
good, okay.
Do you take into consideration these properties of two magnetically different water molecules, and of course their population, because ortho and para water may be looked upon as small magnets and small dielectrics and so on. So these are my two questions. How your concept, how your theory allows us to move into explanation of these novel properties of water and unusual properties of water.
The first question was about the electromagnetic, the effect of the electromagnetic on water.
Ortho and para.
Not only electromagnetic fields on water, but electromagnetic fields in relation to very high dilutions of solutions, which, for example, you go below nanomolar concentration or 10 to the minus 9 concentration, sometimes below 10 to the minus 7 molar concentration, and without external electromagnetic field, there are no nano associates in water. And other structures, they do not appear. That's what I mean. This is the series of Cannavalo's discoveries.
I know. Yeah, yes, but I do not have a conclusive opinion about it. My point is that I can understand what I can measure. And it's difficult to do some experiment about this. So how we can do an experiment in order to understand what is the behavior of water when submitted, when exposed to electromagnetic field. I did something many years ago, just studying the effect of electromagnetic fields on, or magnetic fields, low frequency, on a solution of amino acids. And studying the effect on amino acids, I can infer something about the properties of water, because it's very difficult to understand what happened to water. So I put a perturbation in water and study the effect on the perturbation. And we found that there are effects. There is a change in the properties of the amino acids in solution in water when exposed to a magnetic field. But it was just the beginning of a path. It's necessary to do more and more in this field. So I have no conclusive idea. I know that there is something that happens in water when it's submitted to a magnetic field. And it's possible to see it just observing what is dissolved in water, not looking directly to water, looking at the perturbation. So this is my point.
Second, my question was about orta and para water. Do you take into consideration?
I'm sorry, but I have no idea. I try to study the problem, but I don't know. I have no answer about it.
This is really nice that you're mentioning it. We have one webinar in plan to ask actually a person who can come and talk about. That was basically 2 webinars after this we have in plan. So maybe we will have a better image. Thank you.
Thank you.
So Antonella, we now have a lot of questions from Pierre. Pierre, would you like to actually ask those questions yourself? Yeah.
So hi everybody, can you hear me?
Yes.
Perfectly.
Okay, lovely. Welcome. Wow, fantastic, Antonella. I'm just smashed somehow because at a certain stage I lost you. I got stuck with Giuseppe Vitiello's intervention on entanglement. But before we go on that, I would like to pick up slide 34, where you show the Kramers-Kronig relation and the Xi-Omega extension. Maybe you can open up slide 34. Or I have a screenshot if you want. I can put it on.
Okay, Pierre, if you can share.
Yeah,
quickly.
then I go start screenshot, screen 1. Allow. So you probably should see. Yeah. There are several issues that struck me. I remember I have stumbled over this already in the past, and we talked about it, but maybe it slipped my attention. And one is we have the real part, the real and the imaginary parts of the permittivity is plotted on the screen versus frequency. And if you go all the way to the terahertz range, you can see that the coherence fraction here on top goes down. When if you do the classical fit, probably is, I think this is the classical fit without doing the Xi-Omega extension, right? The double dBi extension. Is this correct?
The blue one is the coherent fraction, and the pink is
the dash. Okay, on the dash line up there.
The dash line. I don't remember, but you see the light blue is about 80 at 0 frequency.
Yes, exactly.
Constant. Yeah.
So which means this is the fading off, the dissipation, whereas in the imaginary part we have the dissipation heat, right?
Mm-hmm.
So this means the non-coherent fraction is right below here. Yeah. So in this case, we see a dominance of the coherent fraction versus the non-coherent fraction versus the frequency, and the mismatch that we have seen without using the Xi-Omega extension up here actually would have suggested the inexistence or.
Sorry, Pierre. The addition is only in the imaginary part. We have to have the
imaginary part. Yes.
Yeah. This is the mismatch. Because we need an addition only in the imaginary part. This is the point. This is the violation of the
this error system, the thermal issues, not the thermodynamics issue.
Mm.
So which means in this case, we even can say that deducing that this better fit from your extension that you have done up here, actually down here in this one below, which means now we have solid, firm confirmation that there is coherence taking place.
No, I don't understand.
That this is an extra confirmation, the extension is an extra confirmation that coherence is a fact. It's no longer something hypothetical.
Mm-hmm.
So we have a biphasic system, a two-phase system of water.
I'm
Right?
a little bit, so I really don't like that we use the same words for many things. I mean, can this really be called just fractions, coherent and non-coherent, and not coherent phase? Because
no, the point is that now we have firm evidence that we can no longer deny the coherent fraction. There is a coherent fraction there. I think this is proof.
Yes,
this is one aspect.
In my opinion, this is self-evident somehow. I did not.
Well, maybe just okay.
The point is the following. We are looking at experimental results. We were not able to fit the results if we use the old model, not the double, the bi, or even the triple, the bi. They use up to 4 different terms with many parameters. Okay. Now we are able to fit the data just applying the old model to a different system, and the system is made up of 2 parts that we have identified with other experimental system with a coherent or correlated, up to this point, correlated and non-correlated phase. So this is what we are seeing. If we assume that our system is made up by 2 different parts, one correlated and the other one non-correlated, we are able to reproduce the data, to fit the data, the experimental data. But there is something more. In order to have a very precise, a very good approximation, we have to introduce another term, this C omega. What does it mean? It means that there is a violation of the causality term. Then the only system able to support a violation of causality is a single quantum system. So this is just an hint that there must be another description of the system. We have to use quantum mechanics in order to justify this term here. Otherwise, it's nonsense.
Okay, this helps a bit. I didn't get everything, but this helps a bit. Maybe we do this in a private session. And the other thing is, because Giuseppe Vitiello mentioned entanglement, is there a relation between the coherent phase and the non-coherent phase in terms of entanglement or not?
I don't know if Giuseppe, if Peppino mean an entanglement between molecules.
Entanglement is, yeah, okay. Antonella, before you were mentioning that one cannot think in terms of one single molecule just in a previous comment of yours. And now this means that we do have collective modes. Entanglement is between collective modes. Indeed, that Z omega term, that is crucial, as you are saying, because it shows that you are dealing with a quantum system. That Z omega term is, in technical terms, usually forgotten, even in a quantum optics treatment. That is, it's called round wave approximation. But that is exactly the term that controls the change of degree of coherence. each degree of coherence is a sort of a phase for the system. So you have a system with many phases, many dynamical regime. Due to that Z omega term, indeed, you were saying before, is imaginary one. And this means that it is a non-unitary, you have a non-unitary process. Mm-hmm. So you have a typically phase transition if you consider that term. And that is a very important term, which appears only when you do quantum field theory, not just quantum mechanics. So that is about that. But what Vladimir was asking before about electromagnetic field and coherent phases. We, with a long time ago, even before then, Giuliano Preparata was coming to Milano. It was in 1986, a long time ago. We did compute the inner, with Emilio Silviadoglia and Marziale Milani. There is a paper on nuclear physics, 1986, I remember. We did compute the inner diameter of the microtubulus. That is a computation which is nowhere, nobody did. But we could be able to do it by considering the interaction of electromagnetic field within coherent water. And it comes, in fact, 14.6 nanometers. I remember because it was shocking for us that we could be able to compute something which is nobody has computed still today in any means. And that is due to self-focusing of electromagnetic field without a coherent medium, like water in this case. And so this is a crucial problem, one of interaction of electromagnetic field with water is a really crucial one. Without talking of the fact that electromagnetic field is trapped within coherent domains, as we know.
Thank you, Professor Vitale. Pierre, does that answer your
part of it? I'm just still boiling. It's since this is so special and so, I think, fine detail that I need to elaborate just rereading the paper that is quoted on the screen. But again, coming back to the previous topics that I just put in the chat, is can we, if there is this kind of entanglement, can we, and this goes hand in hand with the question of Vladimir, goes hand in hand in that, can we talk about ultra-high dilution and entanglement as an effect to explain a memory-like behavior?
I have no answer.
Pierre, you have to do some experiments, I think, for all these questions.
I have something in mind using the Jardine effect, but this is not yet hammered out properly. So
on the basis of what we are able to see and to study, I assure you that if you look at the details, you can have a lot of information. Let's look at this small term Xi omega. That's very small and it's very you can avoid it if you want. But if you want to obtain exactly the experimental result, you have to include it. So if you do a good experiment, you find something very important. This point is the first strong hint that you are dealing with a quantum mechanical effect. And the second one is the effect about the restructuring of water in self-similar way. It was obtained just looking carefully at the experimental data and looking at the deformation. So if you look at the experiment, you can find really a realm of information. There's a lot of information, there's a world of information, but just starting from the experimental results. So I'm not in position to answer to your question.
Yeah, but at least thank you so much for that intermediate explanation, because it helps me to focus on it. This is something important that I need to look at very, very closely and try to understand it properly, because it seems to me quite important.
Yes, yes, definitely, Pierre. Thank you.
We have,
sorry. Yes, yes. I'm sorry.
Go ahead.
Well, there is a question in the chat box, but if you have comments with this,
yeah, I was listening to this, and I remember the question from Alexander. And it is good if we can go towards a kind of common perception for the water. So I think at this moment, including our experimental data also, that and log plot, etc. So what I just wanted to confirm with Antonella, to me, we have quantum domains, we have water molecules, well, let's say hubs. Yes, exactly. I think the word hub fits. That vibrate with specific frequency, and we have a range of those frequencies. We experimentally we can see very nicely that above visible range, even above 1100 nanometers, we start observing the presence of coherence. Means that with those frequency, we have water molecular hubs that vibrate with this coherently at these frequencies. And that was my very first question about this energy gap. So what I imagine is that we have these hubs, water molecular hubs, vibrating at specific digital, I would say, frequencies coherently. But we have non-coherent frequencies, and we could even now name it that this is water dipole. At the moment, we call it water dipole, two water molecules.
Dimer,
there's no,
sorry.
I don't.
Dimer.
Dimer.
You said
dimer.
dipole.
Sorry.
Dimer.
Oh, dimer. Sorry. Thank you. Dimer. Well, we don't know why. Maybe at a certain point we will know. But water is non-coherent. There are 4 nanometers only where water shows non-coherence. Yes, we observe this quantitative difference in the number of the population, the molecular population in these 2 different liquids, as you call them, which I still want to understand what is the reason why we have. But probably we start understanding what each of those frequency relates to, and maybe someday we will understand this. But there is no doubt that we have, and adding different components to water. I'm talking about pure water at the moment, but adding different molecules to water or different perturbations to the water changes this molecular. How to say this population, the hubs, the population of hubs vibrating at specific frequencies. Yeah, I think this is the image that I have at the moment, and this is real. So
yeah, yes, I absolutely understand what you wanted to say, but I don't. So maybe we should actually prepare also the webinar, and share what we this. So.
No, but it is now it is important with Antonella to be on the same page and to see where the difference is, if there are such.
I like, so I mean, if you do not have anything else to comment, actually there is a comment in chat box which is related to what you were saying, and this is an interesting comment, I think, and we did some work. So Graziano, could you please just ask in real time?
My question was about the different densities of the 2 phases of water, and if we can do anything about manipulating these 2 phases by acceleration forces. So I was thinking about centrifugation, centrifugation processes, if we could aim to separate or maybe create some sort of effect on their equilibrium due to acceleration.
No, well, there is a difference in density because as I show you the mean radius of a molecule in a coherent phase is higher than the mean radius of the molecule in isolated states. So the density is lower in the coherent states. But the two phases are not stable. They are not thermodynamic phases. I mean, water and ice. So it's impossible in principle to separate them because each molecule behaves to a coherent or non-coherent state just in a statistical way. So it spends part of its life in a coherent state and parts of its life in a non-coherent state. It jumps up and down, in and out in the coherent states. This is the reason why it's impossible to see with eyes the coherent phase. Even if you use an atomic force microscope, you cannot see the coherent phase.
Of course, my hypothesis wasn't about sorry.
Excuse me. The only way to see coherent phase is just with spectroscopy, because spectroscopy just counts the number of chromophore in a certain state of energy.
Exactly.
But the total number, not the single. If the single molecule is inside or outside the state, it doesn't matter for spectroscopy. It's not interest. Spectroscopy doesn't see the behavior of a single molecules. It just gives you the global number of molecules in that state. This is why it's possible to see coherent and non-coherent only with spectroscopy and not with microscopy. Because microscopy just look at stable states. So it's impossible to separate them with a centrifuge or...
I don't want to separate the two phases. I would like to understand if an acceleration could deform the equilibrium during the application of the acceleration. So the hypothesis was to look at the solution while the acceleration was applied. I don't want to separate the two phases.
In principle, but it's very complicated. I cannot understand how it could be possible.
We should look like
the acceleration.
We should observe the centrifuge itself.
No, can I add a little bit to this discussion, Antonella? I think that, Graziano, the question is, can we control this coherent, or maybe how to increase the population of coherent states, right? Is that your question? What kind of perturbation can we use for that?
It could be a point, a way to apply, in some sense, a force on this structure of water to trying to affect the structure with another means, with another way.
Yes,
not
absolutely.
absolute, not temperature, but we could say stresses.
Light. Well, I would say light. Light is a beautiful tool to change the coherence in water.
Excuse me.
Light.
Light.
Maybe
Photons.
I
Light at different frequencies.
heard about it. It's fantastic. Thank you for the suggestion.
Yes.
And I already heard something like that, probably from Antonella.
I actually like your question very, very much, Graziano, because what you said here, you mentioned centrifugation, and that this is really, to separate this. And the interesting thing, what we have, not actually centrifugation, but with filtration and with vortexing. I mean, this really processes that we use for separation. We, the highest influence of these techniques, those are mechanical perturbations, is actually on this, let's say, this non-coherent part. This is the part of water that is most influenced. according to our experiments. And this was really interesting now when I saw your question, that we are altering the way because this, let's say, non-coherent fraction, if you think it is around isospastic point, you're directly influencing how these two high and low density states are going to actually be able to switch from one to another.
Yes.
So that was really.
Livio is here. Livio is here. Hi, Livio.
Hello, Professor Giuliani.
I would like to comment the last question and a question, the second question of Vladimir Voyekov. When we have a high dilution, very high dilution, the behavior of water changes from many points of view. It changes conductivity, it changes pH, index, refraction index, and so on. Why? Because there is an interaction with electromagnetic fields that usually there isn't when you have high concentrations. This is due to the fact that the KT is no more caused by molecules of several species that usually are in water. The point is that there is an interaction between coherent domains in that case and human frequencies that provokes the release from coherent domains, the release of hydrogen cations. And this fact implies that that water has an increase in conductivity. Furthermore, this fact causes another phenomenon that when you apply a strong mechanical push, a strong mechanical impulse, this impulse is transformed in a electromagnetic impulse at the same frequencies of the mechanical impulse. Why? Because there is water is in a static magnetic field, and the movement of the ionized water that has many hydrogen cations causes a current that is accorded, that is in agreement with the frequency of the mechanical vibration, if you put a mechanical vibration. So we can say that the situation is that when you have a strong dilution, there is also a different behavior of water related to the interaction of coherent domains with electromagnetic fields in very low, in extremely low frequency. This is what we can say on the basis of a experimental work we published in 2015, also signed by Abraham Liebov, with the first name Enrico D'Emilia, and where we illustrate as all stimulation water in that condition, all simulation water is transformed in electromagnetic fields. I hope to have.
Thank you. Thank you, Olivia.
Thank you. Thank you, Professor Giuliani.
Thank you.
Okay. Do we have more questions, more comments? Pierre, any last thoughts?
May I add something?
Of course, Antonella.
There is someone interested in continuing the work on the violation of the Kramer screening and the causality relation. I should be very interested in continuing, but I need some help because I need someone else interested in this topic. So if there is someone interested in, please let me know it and we can continue.
Wonderful. Wonderful. We can go together somehow. Yes. Very good, Antonella. Thank you.
Thank you. That is beautiful. So whoever is interested, just go ahead, contact Antonella. Any more questions? Pierre. So Pierre will be joining you. Pierre wants to do everything. I don't know how you manage. Graziano had something else about mechanic to electric conversion. This is understandable by the difference in density of the two types of water, so that they will be subject to different amplitude in vibration and the related electric. Okay, this is a comment.
It's a simple comment.
Thank you, Graziano. Professor Olivia Giuliani, do you think you can please send to us, to our email, the reference for the paper you mentioned?
Yes, yes.
Beautiful, thank you. And we will share then with the rest of the people. So last chance. Any last comment or question? Anyone? Well, Professor Vitiello, yes, please. Professor, sorry, microphone. Microphone, please.
Yes, I'm sorry. I would like to add one more little stone supporting Antonella presentation. The fact that we might have a coherent structure for water in together with a non-coherent one, I mean in this double liquid picture, also fulfill a basic thermodynamic law, namely the minimization of free energy. In fact, one can show that temperature will be inversely proportional to the size of the coherent structure, of the coherent domain. And if one works out, I mean, just a little bit of mathematics, finds that this relation is exactly equivalent to minimization of free energy. This is something, this relation is also that relation in that old paper I gave you the reference in 1986. But only recently, studying behavior of trees in Val di Fiemme forest, together with some experimentalist colleagues, I realized that that relation is equivalent to the minimization of free energy. And to me, this is really satisfactory because it shows that above and beyond any specific modeling, coherence of water is a crucial behavior of nature. Is not so, and by the way, it is Alessandro, I do not remember his last name, before he was mentioning about such a problem with coherence and so. But coherence of water acts as a moderation of the randomness of chemical reactions. Because here there is the old question put out by Schrödinger in What is Life? It's not possible to consider biology as regularity only in the average, as it would be on a statistical basis of just biochemistry. So these features that are appearing now more and more, especially with experimental works, not just theory, as Antonella is doing, but also Rumiana and other ones working experimentally on water, they are crucial to understanding of biology. This is my comment, yeah.
Right.
Thank you for the comment, Professor Vitiello. Yes, I absolutely love this. I mean, we're all actually studying this because we want to know what are the effects on biology and what can we actually learn about life. And this is all. This is the purpose. This is the aim, I guess. Okay, then, well, let's say we have extended this webinar way. I think this is the longest record so far. I have never been this bad before, but I really enjoyed. And Antonella, I wanted to say, this is the first time that I actually really, I very much appreciate your presentation. This is the first time that I, let's say, I'm sort of like allergic when people are starting to talk about self-similarity in water coherence and so on, because I hear a lot of empty talk. And this was the first time that I absolutely understood almost everything that you said. And I really love your approach, how you say, this is what I measured. These are my experimental results, and this is it. And I'm not even, like, I don't even want to go into, imagining maybe this is, like, maybe this implies that. No. This is what it means. I know this much. I love that. I really hate speculations, especially on, so this was really beautiful. And I'm very grateful that I was here to hear this talk. And I really thank you to all the people who came and participated in this lovely, lovely discussion. Really, we broke the record today, and I'm really happy that this was of interest to all of you. So maybe in future we could also go back to this topic a little bit more. Maybe Professor Vitiello can educate us a little bit more about self-similarity. We would love. I think most of us really lack some better background in this. So it would be good to hear. So, Professor Tenko, would you like to comment something for the end of the webinar?
No, thank you very much for the hard work, Jelena, and Antonella. Thank you very much for beautiful. Exact. So, but we need both. We need to imagine things, Jelena. So we have to.
Okay, well, just I hate what people are. So of course there is no new thing without imagination. I'm allergic to basically using scientific terms for wrong reasons, like some egoistical claims and so on. This is something that I really don't like. And especially this quantum mechanics, quantum electrodynamics, and those phenomena which we still don't understand are misused by many people. This is what makes me. But other than this is what I really, really appreciate when I hear a scientist like this. I measured. This is like objective. This is a number, and this is what I see. And you cannot actually, argue with that. This is the most beautiful thing. I love that. That's discovery. We have to rely on what we measure. So this is beautiful.
It is modern, maybe, to talk about quantum, etc. But we don't have enough. So we have to work hard to make vocabulary.
That's right.
And,
yes.
Backed up vocabulary with real data, with models that fit the data, and then that people easily will learn about. And because I was so happy to see Pierre saying Oh, now we have a coherence in water. Yes, we know. At this meeting, we know that water is coherent, and there's a coherence. But we have to find the right way to everybody to know what water is, because it's really crucial for understanding our living systems. Thank you very much for your contribution. Antonella, you're very welcome to join us, and we will be happy to join you to continue and just work on further, deeper and deeper on the experimental data calculations and modeling as well. Thank you. Thank you all.
Well, then with this, we are closing this webinar. Antonella, thank you so much. Thank you, all of you who came here today. It was lovely, lovely, really. I'm happy to see you. So then, until next time in June, we will be going to some less, let's say, maybe less interesting topics, more about aquaphotomics. But this was really today brilliant. I'm very, very happy.
Come on, it is interesting.
This was super interesting.
Yes.
Bye-bye. Bye-bye, everyone.
Take care.
Bye-bye.
Thank you for coming.
Bye, Yoko-san. Oh, Elmer.
Hi, Elmer. Hi.
Oh, Sato. Bye-bye. Bye.
Oh.
Goodbye, Professor Julia.
Konnichiwa.
Bye, everyone. Bye, Tomoko.
Bye, Tomoko.
Bye. Goodbye.
Thank you.